among you remembers that very specific instant when our teachers made us cut different shapes into halves as little kids? Achieving a perfect and equal half was, if I must say, one of the most nostalgic experiences a child can have in his life. If I can remember it correctly, that was the very first moment symmetry was introduced to us. We learned that a shape is symmetrical when its half is equal to the other half, as if mirroring each other. But is symmetry just all about that?
Ian Stewart provides us with a different perspective of symmetry in his book, Nature's Numbers, particularly on Chapter 6, Broken Symmetry. Commonly, symmetry is described as a phenomenon when any object has identical or balanced proportion in its halves, which Stewart himself described as bilateral symmetry. He defines symmetry as the phenomenon wherein an object or shape becomes exactly like another even when you move it in some way, whether you turn it, flip it, or slide it. Herman Weyl and Richard Feynman share the same idea as they see symmetry in things that have been subject to a certain operation and appear exactly the same after that operation. Such operations in the eyes of Stewart are what we call transformations.
Stewart presented us with three common transformations: reflection, rotation, and translation, which further explains the concept of symmetry. Reflections or flips are also known as bilateral symmetry. It simply is a mirror effect, or when one object is reflected across a plane to create another instance of itself, like the shape of a heart, a butterfly, or even the human body. Meanwhile, turns or rotational symmetries occur when you get the exact same image of an object when you spin it at 180 degrees. These occur to shapes like squares or circles, or in natural things like starfishes or flowers. Lastly, translations or symmetries wherein an object slides or is relocated to another position while maintaining its general or exact orientation. Stewart called this kind of symmetry as the rule for moving things around, which creates repeated units on the plane like floor tiles or wall bricks.
Almost in any aspect is formed and built through symmetry. With that basic foundation, nature has been filled with symmetry in every way, as present in various patterns occurring all around us. Just like how Stewart saw symmetries in the human body, the petals of a flower, the honeycomb of bees, and even in the structure of the subatomic particles of the universe. But why aren't they obvious enough for us to see?
Stewart showed us how symmetries are present in what he called planned uniformities. Simply speaking, he tells us that nature's symmetries are so perfect and extensive that every point it contains is highly equivalent to each other. Such points are arranged in a specific order, thus creating series of patterns in it. These points look extremely the same, interchangeable and replaceable, that we fail to notice the presence of patterns. The existence of patterns in such natural occurrence is what makes up symmetry. But another question comes up in mind. Where did these natural patterns come from?
Stewart further discussed to us the concept of broken symmetries, the main idea of this chapter. He used throwing a pebble into a pond as an example to visualize this idea. The pond has so much extensive points in it that we only see it as a flat body of water without seeing different patterns existing in it. As the pebble meets the surface of the pond, we disturb and lose all its symmetries except for the point where the pebble strikes. Altering the original state of the pond created a pattern of concentric circles that we see as ripples in the water. This is the same as the formation of dunes in desert sands. The wind flows like a fluid in the flat plane of sand particles, therefore breaking the perfect symmetry of the desert and leaving a trail of dunes.
This phenomenon, the breaking of symmetries, can explain why we see a lot of patterns around us, as Stewart claims that the symmetries we observe in nature are broken traces of the grand universal symmetries of our mass-produced universe. At the same time, he used broken symmetries to unify what at first sight appear to be a very disparate phenomenon. He tells us that mathematics, through the symmetry-breaking processes, can explain in a unified way the fact that the patterns we see in dunes and zebra stripes are caused by processes that, while physically different, are mathematically very similar.
The mathematics of symmetry and symmetry breaking have been widely used and applied in the field of physics. especially in stabilizing various theories and scientific studies. One of the said theories is the Goldstone theorem. Basically, the Goldstone theorem opens the existence of small, massless particles called Goldstone bosons, which arise from one ground state breaking the symmetry of the other ground states of an object, creating different levels of energies in it. Continuous symmetries on the object are spontaneously broken. Thus, energy currents are conserved but still leaving the ground state invariant under the action of corresponding charges.
Coleman-Mandula theorem is yet another scientific concept that applies the mathematics of symmetry. It concerns what symmetries are possible in a relativistic theory of interacting particles, and according to proponents Sidney Coleman and Jeffrey Mandula, space-time and internal symmetries cannot be combined in any but a trivial way because the symmetry of a vacuum is the symmetry of the world.
Symmetries are even linked to the law of conservation, stating that certain quantities can suddenly vanish or be created from nothing. For example, the ball won't start moving unless it is kicked. Momentum is something that is always conserved. In 1915, mathematician Emmy Noether linked those conserved quantities to symmetries and proved a deep result to her theorem. She said, conservation laws are equivalent to symmetries in the laws of nature. Every conservation law comes with a symmetry and vice versa.
Other than science, writer Robert Kuhlman described the underlying mathematical principle behind all patterns and symmetries as important in art as it is applied in architecture, pottery, quilting, rug making, and the like. In the words of Herman Weyl, the notion of symmetry carries with it the connotation of beauty, harmony, and unity.
As Stewart concludes chapter 6 of his book, he visualized an ideal mathematical universe in which all of the fundamental forces are related in a perfectly symmetrical manner. He left us marveling upon the idea of the Earth being a different world if the symmetries of the universe were broken in a different way. Furthermore, he made us reflect on the fact that the most basic method of pattern formation, the same mechanism of symmetry breaking in a mass-produced universe, is what governs this whole universe with everything in it.
Broken symmetries of Ian Stewart allowed us to see the beauty of symmetries in a completely new perspective. This chapter represents that all the patterns we see have undergone processes in a unified way to look at what they are now. They are diverse and disparate from each other. Though they may seem obviously different, they are actually similar in a refined sense. Basically, symmetry unifies an observable event where at first seems to be unlikely. It is astonishing how symmetry in mathematics is present in the smallest up to the largest scale in nature.
Probably right now, nature's numbers have brought us to a point where we became aware even of the infinitesimal patterns around us, which we have learned are the primary foundations of the symmetries of nature. No matter how big or small that pattern may be, they can never be ignored because they make completely different things mathematically the same. Stewart even tells us that the mathematics of symmetry can explain in a unified way the fact that the patterns we see in dunes and zebra stripes, the varying products of broken symmetries, are caused by processes that, while physically different, are mathematically very similar, thus harmonizing the different elements of the world into a unitary whole.
This creates a major impact on us, especially as human beings. For years, we always fight for the unification of a wide array of diversities, whether it may be language, culture, or race. But then, as we further develop our understanding about nature, through the mathematics present everywhere around us, we see a silver lining among our individual differences. At some point, a perfect mathematical symmetry highlights our similarities as persons and binds us as one.
I and Stewart have been very generous enough to allow us to see the world in a mathematician's eyes, no matter how much we deny it, no matter how many people dislike mathematics. The whole world feels a lot different seeing how even the smallest aspect of math keeps the whole world going around.